Okay, good afternoon, everyone. Can you guys hear me? Okay, great, thank you. So before the lecture, two quick announcements. The the project proposal is gonna due today. So please make sure you submit your proposal report on time. And also the second, we'll have the office hours starting next week on Tuesday from 10 to 11. So I check my schedule. That's like the most convenient way I can host the office hours, so I don't have to, rearrange some of the meetings. So I'll send out an announcement, and we'll do this in Canvas. So every time I'll initiate a conference. So if you have any questions later during the class, right, the presentation, or maybe you have questions about your project in terms of progress, you can join the meeting, ask those questions. Okay.
Like I have one question regarding the selections. Like, do we have to select the best research paper or a particular data set and try to improve that, or take a paper that is published around last 1 year or 1.5 year and try to apply that and improve that?
So you mean the project?
Yeah.
Yeah, so I think you don't have to select like what's the latest or maybe the newest paper. So you can basically find a paper, maybe the most recent ones, not like maybe 5 years ago. I think they may be too outdated. And the idea is that see if you are able to, challenging yourself, maybe make some of the improvement over it, right? Some of the techniques you learn from this class, or some of the papers you read. Okay. Okay, all right. So let's begin our lecture today. So for today's lecture, we'll talk about self-supervised learning. So there's several categories, the general categories of machine learning. So most, the main one will be the supervised learning and the unsupervised learning. Okay, so for the supervised learning, which we, have known this, a lot, right? So the basic idea is you will have some supervision, right? That is in the presence of like training data, right? For example, you do image classification, then you have a training data set, and each training sample is going to be associated with a training label, right? Which class this image belongs to. And this training data or the labels will be usually going to be annotated by humans, right? The human labelers will, annotate, right, what is the label for this particular image, right? Once we have this training data set, we can train a machine learning model and deploy this model on some of the testing data, unseen data, okay? There's another major category of machine learning model is targeted at unsupervised learning. Basically, you don't there's not any guidance or supervision. So basically just give you a bunch of data, right? You wanna maybe using machine learning technique to discover the patterns, right? So one example is the clustering, right? So I give you a bunch of different, data points like this, right? Maybe can you discover some of the patterns, right? So, so here you can clearly see these data points kind of scattered in these kind of two clusters, right? So maybe I can using some clustering algorithm like k-means to classify to cluster these data points into these separate categories. So in between the supervised and the unsupervised learning, there's one category called semi-supervised learning. So basically it has, like both of the world, right? So it has a small amount of label data, right? As compared to supervised learning, right? The semi-supervised don't have a lot of label data, maybe because of the, the labor issue or the cost issue, right? A lot of industries, right, maybe cannot afford the labor and the cost to annotate a lot of data, but you do have some, small budget, right, to create a small set of label data, right? Not a lot, a small set that is doable, fits the budget, you can do that. But at the same time, you have maybe have a lot of unlabeled data, right? And you also want to leverage those unlabeled data to help the machine learning algorithm to learn better, right? So for this type of learning paradigm, you have both labeled data and unlabeled data. You want to learn them jointly to discover some of the patterns, right, for different applications. And in between, we also have some of the learning paradigm called weakly supervised learning, which we talk a little bit about when we discuss the network interpretation, right, using class activation map gradient CAM. Right, so the weakly supervised learning, again, address the issue of this kind of cost, labor intensive labeling for the supervised learning task, right? So here is an example of semantic segmentation, okay? And as you know, semantic segmentation, doing some labeling is very time consuming, right? Because you have to, annotate each pixel in this image, right? Which category this pixel belongs to, right? If this is a large image, then one human labeler may spend a lot of time, maybe 1 or even 5 minutes, maybe to label this data, if this is a very complex thing. So for the weakly supervised learning is that, so the idea is, can we provide some of the weak label, right? So one example is, can I just, label the class, the classes of the object in this image, right? Maybe I can label this as a cow. There's a, maybe if there's other animals, maybe like a horse, right? I just label this object level label, right? Instead of pixel level. Then I will using this weak label information to, perform the semantic segmentation task, okay? And on this one, this is another example of the weak supervision signal, right? Instead of label every pixel in this image, in this method using scribble annotation, right? So the human labeler basically just, quickly draw a scribble, right? This is the grass region, so I just quickly draw, no matter how you draw it, right? You just quickly do this. And this is the region of a cow, right? I can just, draw a line, draw a curve, whatever, just, within this object region, right? This is a tree and this is a sky, right? So in this way, you at least have some annotation, right, for each of the class, right? Not all the pixels, but some of the classes here, right, is labeled tree, and some of the pixels is labeled as sky, right? And they also have some, regions, right? So trees kind of across these regions, and the sky kind of these regions, and the grass here, right? So these are considered weak supervision. Then you will leverage these supervision signal, then do the desired task, like the semantic segmentation, okay? So another weak supervision you can think about for this, semantic segmentation is, draw a bounding box, right? Or make a couple of clicks, right? So this is also some of the weak supervision signal you can think of, and kind of trying to speed up or make this task easier, annotation task easier. Okay, and the self-supervised learning, which we'll discuss today, is a subset of unsupervised learning method. And this self-supervised learning refers to the learning method, right, in which the algorithm explicitly trained with automatically generated labels. Okay, so here are some of the distinction. What does this automatically generated label means? It compares to the human annotated label, right? Which humans has to go through these data points, right? And based on the human experience or the prior knowledge, and give a label, right? But the pseudo label, the pseudo label, which is used for the self-supervised learning task, is not generated by like human annotation, right? It can be generated automatically by some computer program or some algorithm, right? Through some of the pretext task, okay? So in other words, the pseudo label basically come for free, right? You don't have to spend the time and the cost to generate these kind of labels. So mostly we'll talk about some of the popular pre-test tasks, right? How can you generate pseudo labels based on different pre-test tasks? Okay, so here is the general pipeline for the self-supervised learning. Okay, so you will have, first of all, have the unlabeled data set, right? So you don't have any label information here. And we will, come up with, or maybe develop a self-supervised pretext task for the training, right? So let's just, assuming we know what kind of, pretext task that is, right? Maybe one example could be, image reconstruction, right? Have input, go through the network and trying to reconstruct this image. And we'll talk about many other tasks, different tasks later, okay? So let's assuming we have a defined pretext task, right? We train the network, right? Maybe one convolutional neural networks, okay? So once this network is trained in this pretext task, and we're gonna using these trained network and fine tune it on the downstream task, right? So essentially, this is a knowledge transfer process, right? Using the knowledge you learned from this, pretext task, and you want to transfer this knowledge to some of the downstream tasks. Maybe you have a small labeled data set, you can fine tune it for image classification, or maybe you want to do object detection, etc. Okay. So why, we want to do self-supervised learning, right? So we've talked about, one big reason is we don't want to create this kind of labeled data set, which can be very expensive, time consuming, right? So it requires hiring human labelers, create some GUIs, right? To generate the labels you want. And also, humans may also make some of the mistakes, right? There's maybe some inconsistency or some of the quality issues of the annotation, right? So for some of the applications like healthcare or medicine, the quality of annotation is very important, right? So if you have some of the human errors in your annotation, then maybe your model is not able to learn very well. So that's another potential risk. But for the self-supervised learning, right, we can, take advantage of a lot of unlabeled data, right? So because we don't have to worry about annotate the data, right? Essentially, we can take, if you have enough resource or bandwidth, right, you can essentially leverage the infinite amount of, unlabeled data, which you can, collect from internet, right? For example, image and videos, right? So you can crawl images and videos from internet, various sources like Instagram, Facebook, for videos, YouTube, or maybe other, platforms, right? To, get or collect as many videos or images you want for your task, okay? And also by doing this self-supervised learning on this kind of large amount of unlabeled data, it has the potential of, generate, better, feature representations, rather than you have a decent set of, supervised or labeled training data set, right? Because these unlabeled data may have more diversity, right? Maybe represent better in terms of these kind of real world settings, right? So your learning model could be generalized well. But there's also some of the challenges for self-supervised learning, right? One is how do we select a suitable, pre-test tasks, right, for application, so that the learned representation is meaningful, right? You cannot just like make up some task and hope that learned representation is kind of meaningful for the downstream task or for a particular application. So you have to have a very strong intuition on kind of reasoning behind the pre-task you design, okay? And the second challenge is there's no gold standard for comparison of the learned feature representation, right? How do you measure, how do you compare the representation learned from different, pre-test tasks, right? But one way to measure that is you can definitely, using some of the downstream tasks, right, to measure how good is your learned representation, maybe using the classification accuracy from the downstream task. So so that's the common measure, which the most of the work follow. For the self-supervised learning, mostly considered like two major steps. One is the feature learning process, right? Here we are interested to train a neural network to learn feature representation. And this representation is learned through solving a predefined pre-test task, like for example, image rotation prediction. And then, once you finish the first step, then you want to use or leverage the learned representation or network parameters as use that as a pre-trained model and transfer the knowledge to the downstream task, right? So you can think about these process is similar to the transfer learning, right? So for the transfer learning, we know is you train a model on a large data set, usually, for example, ImageNet data set, right? You're using that trained model and fine tune on your own data set or target data set, okay? So here the difference is that for the pre-trained model, we are not using ImageNet to train, and we are just using maybe leverage even larger unlabeled data set and learn this network through a defined pre-text task, okay? And then we kind of transfer the knowledge learned and to the downstream or your successive applications. So here's basically just a graph illustration of the step one, right? How do you do this self-supervised training using some pre-text task, right? So you have the unlabeled data set, and based on what kind of task you define, right, you can generate some of these pseudo labels, okay? So this label it can be generated very easily by some algorithms or basically come for free, right? Once you have this pseudo label, then the training strategy or paradigm is going to be similar, right, as the supervised learning, right? You basically have an output, right? And this is the pseudo label is your ground truth, and you minimize that specific loss object function. And so there's many different pre-test tasks you can define. And based on this survey paper, okay, and they roughly categorize them into these four broad categories, right? So one is the generation-based method. Okay, so there's image generation, right? You can use GAN to generate image, and super resolution, right? So from a low resolution image to a high resolution image impaling, right? You want to kind of feel some of the unknown regions of an image, which we'll also talk about this later. And image colorization, right? Maybe you have a grayscale image, and then you want to do some colorization for this image. Similar technique can be applied to video generation. Okay, so another category, context-based method, right? So you can define some of the pre-text task that is trying to exploit some of the context information, right? The spatial context, temporal context, right? Temporal context you can explore for videos, right? Frame order verification. And spatial for image, right? So for some geometric transformation, etc. And free semantic label-based method, right? So you can generate some free semantic labels, right? So usually you can, for this one, the moving object segmentation, that is, you can using some of the traditional algorithm, right? Maybe estimate the optical flow, right? Or maybe estimate the frame differences of a video, trying to identify the moving pixels, right? Or the moving objects, right? So this can easily be generated, right? You don't have to do any human labeling, right? You just using algorithm to generate this kind of free label. May not be perfect, but at least have some supervision information there. Okay, so another popular method to generate free semantic label is using some gaming engines. So if you are playing games like the Grand Theft Auto, GTA, maybe GTA 5, right? So those game engines is able to you can generate some of the semantic segmentation map, right? This is a car, this is a road, this is a building, right? And the gaming engine is able to generate image or render a corresponding image has that semantic segmentation map, right? So here, basically, you are using game engine or some software automatically generate like a pair of image, right? You have the image and also you have the semantic labels. Then you are able to using that to do semantic segmentation, this kind of task, okay? And also we have this cross-model based method, right? So one easy example you can think of is the audio-visual correspondence. A lot of videos, footages come with video, right? The frames and also come with the audio, right? So you can you can take this as a pair of information, right? Because they are corresponding to each other. Then you can define a task to do this kind of cross modality matching, right? So here we have two different modalities, right? Audio and the visual modalities, okay? And also this RGB, maybe depths, right? A lot of cameras, for example, the Microsoft Connect sensor or camera, right? This is a RGB plus depth camera, not just providing the RGB, the classic RGB video frames, but is also able to provide the corresponding depth map, right? So maybe you can, define a pretext task, right, to do this kind of cross-model matching, okay? Excuse me, why this? Okay, so next we're gonna, look at some of the representative or very popular, method, how you can define different pretext tasks to kind of do this self-supervised learning. Okay, so the first one, solving the jigsaw puzzle, that is trying to explore the context information. Okay, so the basic idea is you have these kind of different patches, right? And you kind of predefine these 9 patches, and the center, which is these blue patch in the center here, and you can randomly select one patch, okay? And you want to ask the network, right? What's the specific position, right, relative to your center, right? This green one, okay? I mean the blue one, okay? So why this task is able to learn meaningful things is because for a network to able to accurately predict the relative position, right, it has to understand, right, what object it is in this image, right? So for example, this is the ear of a cat, right? So you have to first understand, right, what is this object, right? If you understand this is a cat image, right, then you know some of the semantic structure or information, for this particular object, right? So a cat hand can have two ears, right, the left and the right one. And based on the geometry or the shape, right, then the network has to figure out, is this the left ear or the right ear, right? If the network is able to learn this kind of information, then it is able to make a correct prediction, right? So the correct is the number 3 right here. So for this one, as you can see that the label comes for free, right? So basically you don't do any of the human annotation, right? You can have an algorithm, randomly have a large region, right? Maybe divide this large region into 9 patches, right? Using the center one as the query, and you can randomly select, the rest of the 8 patches, right? And, make as a pair, right? So, and when you generate these different patches, right, the numbering is automatically generated, right? So you know exactly, what number this individual patches, right? So 1, 2, 3. So you can generate these kind of numbering for this, for different patches according to their original location. And this will be served as your label, right? The pseudo label, right? So here, if this is a pair of image here, right? And we'll have the associated label, y is equal to 3, right? If I select this patch, right, I have this pseudo label equals to 1, okay? So what you can do is, for train the network, right, to predict the relative position, right, you are feeding the patch, the center patch, the blue one. Then you also feeding the random select patch, right, the rest of the 8 patches, you randomly select one. And when you select this patch, then you already know the label, right, those from 1 to 8. And you just feed these 2 patches into the convolutional neural network. So this is like a 2 network, the same network in parallel. So this is the Siamese network architecture, which means the same network in parallel. And they have the weights sharing, right? So these 2 networks are identical. So the weights are shared. And so these can be any neural network architecture, right? If you decide to use AlexNet or ResNet, etc. So any off-the-shelf architecture can be used. And the output will be, right, the labels will be, which position, this randomly sampled patch belongs to, okay? So that's the task, pretext task. You can train this network. And once this network is trained, then you can take the representation, right? That's the knowledge you can transfer to some of the downstream tasks. So here's another example, right? So you basically, this is a different image, right? Have an image of as object of a bus, right? You can have this center. For this location, you can have crop these 8 pages in the neighborhood and predict what's the relative location this patch belongs to. Okay. So the author did some of the evaluation, right, to trying to investigate how good is the representation learned by this kind of position prediction pretext task. Okay, so on the left, right, the first column is the input. Okay, and in the second this block, right, the random initialization means this is the AlexNet random initialized, right? Basically, you just using some random Gaussian noise to initialize the network parameters, right? Basically, the network hasn't learned anything yet, right? It's just random initialization, and you take the fully connected layer. They're using the FC6 layer feature, right? Basically, a giant feature vector, and trying to retrieve, right, based on the input, right? I take the features and to find the k nearest neighbor, right? This is the top 5 retrieved neighbors or images. As you can see here, these images basically have different object, right? So it has nothing to do with this input, which is I think this is a motorbike tire, right? And this is understandable, right? Because your network is just randomly initialized, right? There's no meaningful representation. So you basically just randomly, if you're using that feature, you basically retrieve random images, okay? And on the next block here, right? So they have this ImageNet trained AlexNet. So that means the AlexNet has been trained on ImageNet training set, and they're using the train feature to do the retrieval, okay? So here are the top retrieved image. And as you can see that they are, they have the same classes, right? The tire, and I think this is the horse, right? This is the cat, right? As, corresponding to this query input, right? So for the last block here, this is the using their learned representation using this position prediction pretest task, right? As you can see here, also they are able to retrieve these relevant images as to the query input, right? So tire, horse, maybe this is water or lake, cat, right? So that means the network is learn something meaningful, right? Learn some of the semantic information, not, as compared to this random initialized network, right? Just randomly retrieve some of the images, okay? So based on this, kind of patch, the relative location prediction, this paper, they solve the jigsaw puzzle. So which make instead of just, take the 2 patches, right, predict the relative position, right? Is it, which location this patch has been sampled? They take the 9 patches, right? They use all the patches here. And basically you can, just like you doing some puzzles, right? You shuffle them, then you ask a network, right? Can you, piece out all these random shuffled tiles, right? To generate the original image, right? So from here to here, okay? So this also intuitively makes sense, right? So if the network is able to, perfectly assemble these puzzles, then that means the network is able to learn some of the meaningful representation of the object, right? So you have to understand what object that is, right? And also understand some of the geometry or semantic layout of this particular object, right? For this tiger image, okay? So this one actually make the, because they have to arrange the order of these 9 patches, right? Kind of these pre-task is a little more challenging as compared to the previous one, right? You just predict one location of one patch. Right now, you have to figure out what's the correct order for these 9 patches, okay? So let's see how they train the network, right, to solve this problem. Again, the label comes for free, right? So if you generate a large region here and you divide them into a 3x3 grid, and you generate these 9 patches, right? So you can shuffle them and generate a particular permutation, right? So the label can be easily generated. But since we have 9 patches, right? If you shuffle them, then you have a lot of permutations, right? So you have these many permutations, right? To make the task easier, so they they predefine just 64 permutations, right? Not just take these many possible permutations, just predefine 64 permutations and shuffle them. And so the task will be, classification problem, right? Which permutation this input, patch sequence belongs to, right? So this is a 64-way classification. Okay, so each patch will go through the network, right? For example, AlexNet, and the weights are shared, like just like before. All the network weights are shared among all these networks, the same networks. Okay. Okay, so this is just a detailed how they do this kind of training, right? So we have a different patches randomly shuffled and go through this shared Siamese blocks, right? Which means you have identical networks in parallel, and output will be one specific or the predict permutation. Okay. So once the network is trained, and you can, using the trained network parameters, right? So you can freeze the weights, and you can take that network weights and fine tune it on maybe the target data set, right? So you can freeze that, conv layer maybe before the last fully connect layer, right? So maybe your target data set have different number of classes, then you can just train the last FC layer for the classification, right? But you can freeze the other layers which you trained from this self-supervised learning task. And here's some of the result. They evaluate how these solving just jigsaw puzzle, these self-supervised learning task is able to learn how good is the learned feature representation. Okay, so they do this fine-tuning on the Pascal VOC 2007. So the self-supervised learning task is trained from ImageNet, right? You just take the ImageNet training data set, remove the labels, right? Using the jigsaw puzzle, the pseudo labels you generate and train the model, then you can fine tune it on this Pascal VOC and for different downstream tasks, right? So actually they have 3 different downstream tasks. One is classification, the second is detection, and the third is segmentation. Okay, so they compare with the supervised learning task, right? So the first one is the AlexNet, right? They're using ImageNet, using supervised training, right? Which using the label information and using that trained model and fine tune it on this Pascal VOC. And this is the classification, detection, and segmentation result for this kind of transfer learning based on the supervised training. And this, they also compare with different self-supervised learning tasks. Okay. So one here is this one is the, predict the relative position, right? Just one patch. Okay, and the last row is their method, right? To solve the jigsaw puzzle, which is 9 patches. And they compare different pre-training time, right? How long it takes to finish this pre-training task, right? And also evaluate the performance of downstream tasks. So here they were able to outperform, just predicting the relative position for one randomly sampled patch here. So this method, which is colorization, is also explore the context information, right? So intuitively, the pretext task is trying to, coloring a particular input, right? So the input will be if the image is representing this lab space, right? So you can using the lightness component as your input, right? And feed that into the network and ask the network to generate the color component. Okay, so why this works, right? Why the network, why this particular task is able to enable the network learn some meaningful things is because, in order to, get the correct color for different object, right? So the network has to understand, what object that is, right? This is orange, this is apple, right? Then the network can, generate the corresponding color for that particular object, right? To take the colorization task, further. So this paper, they do this kind of half and a half prediction, right? So you have an input image and you separate them according to the channel dimension, right? So you have this grayscale, then you also have the color channels, okay? So for the grayscale channel, they go through an autoencoder, which is the network you want to use, and ask the network to predict the color component or color channel, okay? And also for this color channel part, have another autoencoder trying to predict the grayscale channel. Then you combine them together to generate a predict color image, okay? So you can compare with the original one, right? You can enforce how close your reconstruct image as compared to your original input. So again, here, there's no manual label, right? So basically, we are just doing a reconstruction task, right? Original image and generate a predict image. And we can also using image embedding task as the pretext task for the self-supervised learning. So image embedding, basically you crop out one region of the entire image, right? So for example, here, they crop out a small region in this image, right? So this white region, and feed this image with missing parts or missing region to the network, right? The network has this encoder decoder structure, and the decoder has to predict what is this missing patch, the content of the missing patch, right? So basically, the network has to understand the context, right, in order to generate the region that is missing in this image. Okay, so in their loss, right, because you crop out this region, right? So this one, the original patch is your ground truth, right? So your reconstruct patch can be compared with your ground truth. You have a reconstruction loss, okay? So they also have this adversarial loss, right? You can have a discriminator to trying to determine, okay, is this generated patch look realistic or not? Okay, so that's additional loss trying to make the generated patch looks real. Okay, and here are some of the examples of their the input, right, with one kind of center part is cropped out, and on the right is their generated image based on their network. Okay. So once they train the network using this image embedding pretext task, and they also do this downstream, transfer learning, right? So do the Pascal VOC classification and detection and the segmentation. And the next method using, trying to learn by predicting the rotation angle. Okay, so typically the image will have this kind of their upward direction, right? Then you can rotate the original image at different angles, right? Let's consider 90 degree at a time, right? Then you can rotate into different rotation angles, okay? And this will be corresponding, this will be your label, right? So this is you rotate 270 degree, and this is you rotate 180 degree, right? Here, maybe you can make it this, let's say this is your original, okay? Maybe you can assign a label as 0, right? Rotate 90 degree, this is 1, and 180 degree, this is 2, and this is 3, right? So you can assign this label, depending the rotation degree you have, okay? So if the network is, kind of aware, right, the image is being rotated, right, is able to correctly predict the rotation angle, then pretty much it will understand, right, what is this object, right? What is kind of the scene, correct the scene layout, right? So that's why by doing this kind of rotation prediction task, the network is able to learn something meaningful, okay? So here's their the network for how they are learning, right? So as I mentioned, right, so you have depending on the rotation angle you have, you can have the corresponding label for it, okay? So here they have 4 different labels, right, from 0 to 3. And it will go, once the network is being, the image is being rotated, it will feed that into the network, and the objective is to predict the rotation angle. Okay, so again, this is a classification problem, right? Which class it belongs to, right? Any questions so far?
Then I have a question, like, can you go back to the previous slide? Yeah, here, like, why are they just splitting the model into 4 networks rather than just using only a single network to predict the rotation?
Yeah, again, this is the same network weights sharing, right? So just like a previous one, this is Siamese network, right? So the same network. So you can think about this is just let's say this is just a single network. You can forget about this, right? The single network, you feeding different rotated image to this network, and the objective is just predict the rotation angle, right? These 4 different class labels. Okay, so is that easier for you to understand? Yeah, this is just a rollout, right? Based on different rotations. But essentially, when you train a network, it's just a single network, right? Single network to whatever the network architecture used, then you feed in different rotated images, then you predict the rotation angle. Okay, quite simple, just classification problem. Okay.
And the meaning of shared weights means that it's a single network, and the weights are, so the idea of shared weights is just it's a single network, but images with different more rotations are passed into the network, right?
Yeah, so in this case, basically just a single network, right? Not like the previous one. Let's see. Right, so here we actually have to take like 9 patches, right? So each patch you can consider like a different input, right? So then you have to, based on the information you extracted from all these 9 patches, to make a decision, right? What kind of permutation that is, right? So here we'll just learn, because eventually we are interested is just this network, right? The network parameters, right? Once you learned, you can, using that, this is a pre-trained model, then apply it to some of the downstream tasks, classification, detection, segmentation, etc. Right? So for here, because we have to, take in or process all these 9 patches, so we'll just, each one will go through the same network, right? Same architecture, the weights, while sharing the weights, right? Basically, you don't have a separate network weights for this stream or this stream. Everyone will share the same network parameters. So you can essentially consider them, this is just a single network, okay?
Yeah.
Okay, the next one is learning by clustering. Okay, so this is their general framework, and it's also very intuitively, simple strategy. So you have this input, right? Unlabeled data. There's no, label information. Then you feed this data into the network, some ConvNet. Okay, you extract the features, and once you have the feature embedding, right, and you using some of the clustering algorithm, right? Here you can using k-means clustering algorithm to generate pseudo labels, right? The pseudo labels means the clusters, right? So when you do the clustering, then let's say this for this iteration, I'm generating maybe, let's say 100 clusters, okay? And then I know like which image belongs to this cluster or which image belongs to this cluster, right? So essentially I'm generating pseudo labels, right? I can have a 100 class labels, then I know like which class this data belongs to based on the clustering algorithm, okay? Then I using this pseudo labels, right, to perform supervised classification, right? So I using these generated pseudo labels to perform the supervised classification. So note that these pseudo labels compared to the supervised, the human annotated labels, this one is going to be noisy, right? Because this is based on the clustering algorithm, right? The labels generally may not be correct, okay? But that's why they do this iteratively, right? So once you train the network using the pseudo labels for the supervised learning, then you go back to do the clustering, right? So the next round, maybe your features is better, right? So when you do the clustering, maybe your pseudo label is also improved. The quality of your pseudo label is also improved, right? Then you can using that refined labels to do the classification and do this kind of iteratively, okay? So this is the performance comparison from this deep clustering paper. Okay, they compare with different pretext tasks, right? So here you see colorization, right? So the split brain is, the colorization, right? The gray to color, color to gray, we just talked about. And we'll also have jigsaw puzzle, right? So for ImageNet, they pre-train different pretest tasks on ImageNet dataset, right? Then they using different conv layer features to do the linear evaluation. And that means you just take these features and train a linear classifier and then just evaluate the classification accuracy, okay? So this is their using different conv layers to do the linear evaluation. This is the corresponding accuracy, okay? So obviously the deeper layer present more, higher level representation of the image. You can see, the performance can be improved, right? As compared to the earlier layer, right? Mostly just edges and corners. So the performance is improved when you go in deeper layer feature. And also if you compare vertically, the deep cluster, right? So for individual layer features, they seem to be outperform the other self-supervised learning task, right? So, except the conv1 layer, the jigsaw puzzle is better than the deep cluster. And they also do the transfer learning. So when it's trained on the ImageNet using the self-supervised learning task, and they fine-tune it on the Pascal VOC dataset for different tasks, right? These 3 different tasks. And here I'll also highlight a couple of algorithms we talk about, right? The jigsaw puzzle, deep clustering, and predicting the rotation, right? The 90-180 degree rotation. So it seems like these different pretext tasks, deep clustering is performed pretty well, right? So here, actually the best, right? The second one would be the predict the rotation, right? Also very close to the deep cluster if you compare the classification. And also in terms of detection, right? So they are also, these two are also pretty close. But segmentation, deep clustering seems a little bit more better, a little bit better than the prediction rotation. Okay. So the last one I'm going to talk about in terms the image is the contrastive learning, which kind of gain a great deal of interest in the self-supervised learning field, and is able to have generate very good representations for the transfer learning, and it is published in the ICML 2020. So this kind of animation provide a high-level overview, like what's the idea for this contrastive learning. So they are basically doing some instance discrimination. Okay, so for any of the image, let's say we have ImageNet, right, the training data set, okay, and we don't consider the label information, right, because we want to do self-supervised learning. So the idea is that for one image, right, I do some augmentation, right? So here I do, random cropping, right? Crop a region of this original image. Maybe I resize the cropped region to the same dimension. And then I can do some color jittering, right? Maybe just take the gray component, or maybe just adding some of the some color component, right, to do some color jittering. I can generate an image, right, like an augmented image of the original one. Okay, but one thing to note is that because these content comes from the original image, right? A dog here is still a dog, right? Maybe missing some of the parts, right? For here, they only have the leg, rear leg parts, right? But still, it comes from the original image, right? The semantic information doesn't change, right? It still is a dog image, right? For human, we can recognize this is still a dog, and this one is also still a dog. Okay, so this idea is being kind of mapped and formulated into the learning paradigm, right? So for this to augment image, right, we consider this is a positive pair, right, because they have the same semantic label. So they go through this CNN network, okay? And in the feature embedding space, you want the feature embedding to be close to each other, right? Because they corresponding to the same semantic class, dog, right? So your feature embedding should be close to each other as well, okay? And here, if I take the feature embedding from the dog image, right? And I also have another random image, okay? So this is a chair image, right? Because these two images are different, right? So in the feature embedding space, their feature representation should also far away, right? Because they represent different images. So that's why you'll see like a repel, right? Because these are two different images. So in the feature dimension, you want their distance to each other, far away, right? But for the augmented image coming from the same image, you want their distance to be, close to each other, right? You want to attract them to each other. The distance is going to be small. Okay, so that's the high level idea for doing this contrastive learning. Okay, again, here we don't have any label information, right? We basically just take the original image, do some data augmentation, right? We generate a positive pair, right? And if you select the image, then you randomly select another image, then you can make a negative pair, right? So here is just a more detailed step how you can do this contrastive learning. So basically, you randomly sample a mini batch of n input, and you apply two different data augmentation operations, and you resulting for each one you generate like two copies of the original one, right? Xi tilde and Xj tilde, okay? And you can apply different data augmentation strategies or multiple data augmentation strategies. Here they list a couple of them. And once you go, then you generate the augmented image, then you apply a base encoder, F, right? This is going to be your main network, right? Any CN architecture. then you generate the feature embedding H, right? So you generate a feature embedding. Then you also, after that, you have a, kind of project head encoder. So basically you have another projector to do some feature embedding. Right? So here they are using one fully connected layer to map H to J to Z. Okay. So then, based on because this is the augmented copy of the original X, right? You want to maximize the agreement, right? These feature embedding. And if you have a negative pair, then you want to minimize the agreement, or in other words, you want to push them far away in terms of the distance. Okay. So to measure the similarity, they're using the cosine similarity. Okay, so basically you take these feature vectors and you compute the cosine similarity. Okay, so this is a value between 0 and 1, and the larger means the high similarity these two feature vectors. Okay, then also they have this anti-accent loss function. So that is the normalized temperature scaled cross entropy loss. Okay, so the idea is basically you want to, the positive pair, the similarity gonna be very large, but for the negative pair, the similarity gonna be very small. Okay, the feature similarity gonna be small. Okay. So once this network is trained, then you can using the learned network or transfer the learned representation to fine tune on some of the downstream tasks. Okay. So here is like a detailed walkthrough using example. So if you're interested, you can check this example. Okay. And here are some of the data augmentation strategies they kind of exploited. So they explore these cross and size, flip, color distortion, and Gaussian blur, Gaussian noise, etc. Okay, so which trying to identify, which augmentation, give the best, performance in terms of this self-supervised learning. And this is the comparison of the transfer learning performance, right? So here they also do this kind of two evaluations. One is the linear evaluation, right? So you're basically using the pre-trained weights and just train a linear classifier. And they also compare with the supervised approach. Okay, so they're using ResNet 50, kind of scaled like 4 times, and it is pre-trained on the ImageNet. Okay, so for the supervised, basically you're using ResNet pre-trained on ImageNet, then you do the using that feature embedding and train a linear classifier on these other data set, right? So this food, SAFAR 10, SAFAR 100, these are other image data set. Okay, so they do this linear evaluation and get the accuracy. And this is SimCRR is their method using self-supervised learning, train the features and do the linear evaluation. So it's amazing to see that, right? They are able to outperform the supervised approach, right? Supervised training on the ImageNet. Okay, and also they do this kind of fine tuning, and this is the result they get, right? So on many data set, SimCRR is able to outperform the supervised approach. So yeah, so it's not surprising, right? So why this field got very popular, because of this kind of amazing, people see the potential of this method, right? Maybe someday we don't have to using the label information, right? We can just rely on the unlabeled data, right? To do this kind of self-supervised learning, to learn some very generic feature representation that can be applied to various applications or tasks. So there's also many variants or improvement following this contrastive self-supervised learning approach. So you can go through these references and see, what are some other, method, in terms of this kind of contrast learning paradigm. One thing to note is this SIM Siamese, which is a CVPR 2021 paper. So one advantage is that they don't require negative sample pairs, right? For the SIMCR, we have the positive, right? We want to, kind of attract their feature embeddings, but we also have the negative pairs, right? We want to repel those pairs in the feature dimension. But for the SIM Siamese network, they only rely on the positive sample. So you don't have to worry about the negative sample. So, so you can check out this paper. Okay, so we've talked about a lot of, these kind of pre-test tasks that is defined for self-supervised learning, right? So here, one question is, based on these kind of, ideas you learned so far. So what do you think, there may be some other supervision signals or scheme can be used for visual representation. So do you have any idea, like what other signals can be used or other, supervision schemes can be used to learn some meaningful representations?
I've heard of some that use like natural language processing. So you have like videos and stuff with captions. So maybe something like language is something that can be useful.
Yes. Yeah, that's exactly, in the beginning, there's like a course modality, right? So you can using this kind of multi-model, which has some correlation or correspondence, then you can do some cross model matching, or etc., right, to learn the correlation. Yeah. Any other thoughts?
Do you mean like different kind of pretext tasks for this self-supervised learning?
Yeah. So yeah, I think do you have any other like thoughts or ideas? Yeah, so I think just want you guys to think about this, right? Because I think there's a lot of things, you can take some inspiration from the existing work, right? And to see if you are able to come up something, reasonable, as maybe has a strong supervision signal that can be easily generated and to guide the learning process. Okay. So towards this line, I also want to talk about, we can also using video to provide some of the, rich supervision information to have this kind of self-supervised learning, right? Because for video, we have an extra dimension of time, right? We can actually using time as the natural supervision to guide the network to learn some of the meaningful information there, okay? So for this particular paper, they using tracking, okay? So for a video, right, you can maybe take some of the tracking algorithm, right, unsupervised tracking algorithm, for the beginning of the frame, then till the last of frame, right, to track this particular object, okay? So these another video, you can apply the same tracking algorithm to track this object, right? Basically for each frame, you will have a bounding box for the tracked object, okay? So here their idea is that, so once you learn these kind of different, once you obtain this tracking result, right? And they want to learn a ranking network, right? So basically you take, the first frame of this video, right? And you also take the last frame of this tracked object in this video, and they consider this is a I'm gonna say tracked, not positive. Okay, so this is a tracked pair, right? Then you can take the same, let's say this is video A, okay, just to make easier to understand. So this is video A, right? This is video B. So again, we'll take the tracked object in the first frame of video A, right? Then I'll take another randomly select a tracked patch from maybe from video B or C, just a different video, okay? And I'm going to apply using this as an input, go through the network and learning to rank, which means I want to measure the distance, right? Is this distance going to be smaller than this pair, or this distance going to be greater than this pair, right? So the intuitive idea is that if the object, right, the two patch is coming from the same video, and these patch are tracked patch, right? Then most likely these patch will corresponding to the same object, right? Because of the tracking algorithm, right? But if these two patches are coming from two different videos, right? Although they are tracked object, but a different video, they may track different objects, right? Here, video A, I have a person riding a bike, but here maybe, I don't know what that is. Maybe, I think that's a trunk of an elephant, maybe. But if you think about this is another video, then in this case, this will be a dog, right? And you can imagine that, right? In the feature embedding space, these the distance between these two patches is going to be much larger than the distance of these two tracked patch, right? So that's their learning objective. Okay, this distance should be greater than the feature embedding of this tracked patch, right? So you feed this two patch into the network and learning to rank them. Okay, so that's their learning objective. Also, you can, based on the video, you can predict the temporal order, right? So for a video, I can randomly, sample the 3 frame, but they are temporally correct order, right? Which means I don't shuffle the frames in the video. I just, based on their order, I just randomly select one. And temporally, they have the correct order, right? Then I can also shuffle the video, or maybe just take generate these 3 frames and shuffle their order, right? Then I can have a label. This is wrong or negative, or the wrong label. I mean, the wrong order of these frames, right? So I can just using this as input to the network and ask the network to predict, right? Is this the positive tuple, or this is going to be the negative tuple, which means their order are incorrect. Okay. Okay, so this is their network, right? How they are trained, right? So basically you have video, you can sample 3 frames, right? And form a positive tuple and also form the negative tuples. And then you just feed these input to the network and predict if the temporal order is correct or not. And they also once they train the network, they do some evaluation on the action recognition data set, right? Because this is video, they want to see if the learned representation is meaningful for action recognition. So as compared to this randomly initialized network, they are able to achieve a much better accuracy. So for the image, we have the jigsaw puzzle, right? We can take some inspiration from there and apply it to video, right? So you basically have this kind of 3D puzzles, right? Instead of 2D puzzle, right? You have the spatial, permutation, but you can also have the temporal permutation. Then, the network have to understand, right? What's the temporal correlation and what's the spatial relationship for each individual cubes, okay? And also we can do the cross modality, which you guys also mentioned, right? We can do image and the text, right? So if the data, for example, you cross some images from the Instagram or Facebook, right? They often have like hashtag or something or description for that, right? Maybe you can, or using some image captioning algorithm to generate the description, then you can have like a pair data, right? So you can, trying to predict or do the learn from these kind of paired modalities, Okay, also, RGB and the depth, right? So from the cameras, they have these two different modality generate synchronously, and you can do some modality prediction. Also video and audio. Okay, so for this example, they are trying to do the audio and visual correspondence. So basically you have this input that is video frame and also the corresponding audio, right? So they feed into a vision subnetwork and audio subnetwork because these are the two modality data, right? They're using two different subnetworks to extract the features. And they also have a layer to fuse the feature embedding of these two modalities and ask the network to predict if they corresponding to each other or they are maybe coming from two different sources, right? Maybe this one is coming from one video, the audio is coming from the other different video, okay? So that's these audio-visual correspondence learning. So this is just their detailed network. So for the medical image computing, right? So human labeled data can be very scarce, right? Most likely the annotation is very difficult to get, right? You need to have physicians or expert to annotate the data. And also some of the labels may not, some of the data may not be sufficient enough, right? So we can, using self-supervised learning on some of the unlabeled data to get a very good pre-trained model. Then you can apply it to the target application. Here, I'll just make one example here. And I think this paper you also review, one paper for your review. So this big self-supervised models, advanced medical image classification, right? So this is their general framework. So they first using the unlabeled natural images to do some self-supervised learning, right? Like I mentioned, right? So medical image may, even unlabeled data can be scarce, right? So for some of the maybe particular applications, you don't get to collect a lot of data, but we do have some of the larger scale natural image data set, right? So we can do the pre-training on this unlabeled natural images. Then we can take that pre-trained model and again, do the self-supervised learning on this unlabeled medical images, okay? And once this is basically trying to reduce the domain gap, right? So medical image and the natural image, they have some differences, right? In terms of appearance or semantics, right? If you're directly using the pre-trained on the natural images, maybe there's some, distribution shift, a large distribution shift, right? We also want to do some self-supervised learning on this unlabeled medical images to reduce that gap, right? Once you learn that, then you can take that pre-trained model and fine-tune it on maybe a small set of labeled medical image, right? So for example, this dermatology image classification or this chest X-ray image classification, okay? So they are also using this CMCLR, right? This contrastive learning paradigm, right? So you have the original image, you can generate 2 copies of the augmentation, then you want to maximize the agreement, okay? So this is the contrastive learning. And they also propose this multi-instance contrastive learning. So that means a positive pair is not generated by data augmentation. Maybe for some of the data set, they do have like a pair of image, right? This dermatology image, maybe they have like a left and right hand image, right? So, but they corresponding to the same, maybe a class or something. So you can using that instead of generate another augmented copy. So they, in their paper, they find this multi-instant contrast learning provide better performance, which you can see from this table here, as compared to this CMCR. Okay, so one last thing I want to mention is if you see here, if they are using this SIMCR architecture, right? If you pre-train on the ImageNet, which is the natural image data set, right? And you fine tune on this chest X-ray classification, you can see this is the accuracy you get, right? And if you pre-train the self-supervised learning on this chest expert, which is the X-ray image, and you can see that the performance is able to be improved a little bit, right? And that's what I'm indicating before, right? The natural image and the medical image, there is some domain gap, right? That's, you will see there is some gap in terms of the final accuracy. Okay, if you also follow their method, right? Pre-train on the ImageNet, then also pre-train in the second step, pre-train on the chest expert medical image data set, then fine-tune on the target data set. They also able to improve a little bit, around like 0.3 improvement in terms of the final accuracy. So here are some of just the minor strategies you can explore, right? Based on the application you have, maybe you can have this kind of different steps of pre-training, trying to improve the performance. Okay. So here are some of the reference I list, including some of the popular survey. So if you're interested, you can also go through these surveys and trying to know like what's the latest or the state of the art in the self-supervised learning. Okay. Okay, all right. Any questions?
I have a question.
Yes.
So for the K clustering with the pseudo labels,
Yes.
is there any sort of refinement process to remove bad pseudo labels that have been introduced? I figure after the first round of pseudo labels, your network isn't as well trained. So especially early on, I feel like you're more likely to get some bad pseudo labels.
Yeah.
Is there some way to fix that later on, or do you just have to accept that?
Yeah, I think in their paper, they don't have a particular strategy to kind of refine the pseudo label. I think your questions are very good. And so that makes sense. If we have a strategy to improve the pseudo label, that would be great, right? But I think over time, right, you can think about, I make some mistake, but in order to mitigate that, I may have to train a longer time, right? I just gradually become better and better instead of I can converge quickly, right? If you have some refinement on the pseudo label, I can reach the performance maybe in less number of training iteration. Another strategy I think you can maybe think about this and improve is you can using some ensemble technique, right? So maybe not just one clustering algorithm, right? Maybe several different clustering algorithm, right, to generate the pseudo labels and doing some ensemble learning, right? Maybe just majority voting, right, to make your pseudo label more clean or more accurate, right? So this may be another strategy, to address some of the issues as you mentioned, right? The pseudo labels may not be very clean in the initial couple of iterations. Okay.
Okay.
All right. Any other questions?
You can like here after clustering, we will have that we will do some classification and then we will have some ground truth labels to calculate the loss and backprop the weights, right?
No, I think no. The labels will be the pseudo labels you generate on the clustering. Right, so it's like you initialize the network, right? You feed the input to the network, and you generate the features, and you generate the pseudo labels based on your clustering algorithm, right? And you just treat these labels as the ground truth, okay? And do the supervised classification, supervised training for a couple of iterations, okay? And then you do the clustering again, right? In this time, maybe your label is improved, right? You have a better pseudo label because your feature representation is also, constantly improving, right, during the training. So you do this kind of iteratively, right? So using pseudo label to do the supervised classification is trying to force you to learn better feature. Then maybe your clustering can also be easier to generate better pseudo labels. Then you do this again, right? Trying to refine this iteratively. Okay.
Yeah, fine. And like when you were explaining about SimClear, what they said there are different type of augmentations, right? So in contrast to learning, do they use this set of augmentations every time? So they train the network for 10 augmentations and then they collect the features also?
So in their paper, I mean, you can read the paper to understand some details. I'm not exactly remember every details they have, but they try different augmentations, right? But I think their best choice is apply cropping, then do the color jittering, right? Distortion. So that's their data augmentation strategy to get an augmented version of the original data. So, but they investigate different augmentation, technique, right? Not just cropping, color jittering. They also like filtering, Gaussian blur, adding Gaussian noise, or maybe apply some auto augmentation strategy, right? There's an auto augment strategy that automatically augment image. So they also investigate that. So yeah, so I think these are maybe some. This could be an interest direction you can further investigate, right, to figure out what could be improved in terms of these augmentation strategy, right? Because the learning is based on the augmented images, right? So that definitely will affect the final performance.
Yeah.
Yeah, so I think that's a good point. Then you can, go with their paper and also maybe think about, is there anything, you can do in terms of how you can come up with maybe a better data augmentation strategy for this particular task.
So basically, this algorithms try to augment the data and they try to learn the features that make them look similar, right?
So the idea is that because you look at this X, right, which is the original input, right, you generate these two copies of the augmented image, right? So the idea is that the semantic information doesn't change, right? The dog is still a dog, right? Although you may be missing some of the part, right? The color is different, but the semantic information doesn't change, right? If your network is able to learn something meaningful, right? So the essence of the semantic information of this object, if you are able to capture well, then you should produce a feature embedding, right? For these augmented copy, they should be very close because they corresponding to the same semantic class, right? Corresponding to this original image, right? So that means maximize the agreement.
Sure.
In terms of the cosine similarity distance, which means the distance of these two vectors are very close to each other, okay? But let's say you have another image that is y, okay? Then this could be a totally different image, right? Here is a dog, this is a cat, or maybe a car, right? So consider this as a negative pair, right? If you go through the feature extraction, you generate another feature vector zk, then the features should be far away, right? Because they may belong to the different image, right? In the feature embedding space, you should be far away with each other, right? But for this one, they come from the same image, although it augment a little bit, but semantically they should be close to each other. Okay, so that's their high level idea.
Yeah.
Okay. Okay, so we'll end here. So if you have any other questions, you can go to the office hours and we can discuss there. Okay. Okay. All right. Thank you, guys. I'll talk to you on Thursday. All right. Bye.